I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life,
the podcast that helps you understand the chemistry of your everyday life. And if it's one of your first times joining us, Melissa really is a chemist.
Yes, I really am a chemist. I'm trained in chemistry. I have a master's degree in chemistry. I'm working on my PhD, which technically means you could say I'm an expert. But I do want to remind everyone that just because I am qualified to talk about chemistry and just because I am, quote, an expert, that doesn't mean I know everything. I do everything I can to make sure that I get answers right. But being an expert more means that you know how much you don't know. You're qualified to understand how little you know, more than knowing everything. So I just want to remind you guys about that. Sometimes I can make mistakes. I do everything I can to check my answers and fact check and make sure I'm giving you accurate information. We work really hard to achieve that. But if you ever have any questions or comments, I'm really open to that feedback.
And I am definitely not a chemist. And so all the things that she said don't really apply to me because I don't know anything. So,
Jam is an expert in radio, television, and film.
Yes, that's true. But that doesn't mean I won't make mistakes. So you might hear the occasional... Actually, it does apply. I can say it in my own way.
Yes.
You might hear mistakes, audio mistakes, which would definitely be my fault. And I'm very sorry if you hear those.
Well, today we are going to talk about, on the topic of me having a master's degree, the research I did for my master's.
Dude, nice. What research did you do?
My research was on solar cells.
Oh, dude.
So it's very applicable to our everyday life.
Yes.
And actually, I decided to do it because I have had a few listener questions where people asked what my research was, most recently from Tom T. Mm-hmm. So thank you guys for asking so much. This is a really good topic for learning about chemistry of everyday life, and it's fun for me to get to share.
And I'm really excited. I'm very interested in solar stuff, but don't have any knowledge about how it works. So I'm excited.
Nice. So here's what we did in my lab.
Okay.
We worked on building a better solar cell. So do you know what a solar cell is?
When you say cell, do you mean like an actual cell? Like a little cell with nucleus and stuff like that?
No.
Okay. So I do not then know what a solar cell is.
Perfect. So a solar cell is just a unit that converts sunlight into energy.
Okay.
It's also known as a photovoltaic cell.
Okay.
So when they say cell, they refer to the fact that it's a single unit that can take the sun's light and turn it into energy.
Okay.
So you'll see solar cells on solar panels.
Got it.
Solar panels are the things that are on top of people's houses or in California in those big farms of solar panels.
You can see the cells?
Yes. I don't know if you can see the individual cells, but the things that are coating solar panels are solar cells.
Okay.
I think.
Yeah.
I don't think you can zoom in on the individual. I didn't actually build the cells. There were people who I worked with who did build the cells, but I didn't work on building the cells.
Yeah.
So I worked on the unit that absorbs the sun energy. So we'll talk about that more.
Okay.
There are different types of solar cells in the planet that use different things. But today we're going to talk specifically about the solar cells I worked on.
Okay.
And I think those are going to be the solar cells of the future, in my opinion, because they rely the least on heavy toxic metals or non-renewable resources to make their renewable resource harvesters.
Yeah.
So the solar cells that I worked with used biomimicry.
I remember that from last week.
Yes, I was hoping you would.
Yeah. That's the word, right, for how we are trying to make things waterproof by looking at things in nature that are already very waterproof or water resistant.
Yes.
Right? Mm-hmm. Nice.
Biomimicry is exactly what it sounds. You mimic biology. You're mimicking nature.
Yeah.
So basically scientists take something that works really well in nature and try to recreate it.
Okay.
So one of my very first questions when I came to the lab that I did my undergrad research in was, okay, so if plants are the best harvesters of the sun's energy and storage, which they are, the carbohydrates we eat, all of that stuff comes from plants taking the sun's energy and turning it into storable food energy. Then why don't we just do what plants do? Why can't we just do exactly what the plants already do?
Yeah.
The answer was interesting. It's that we don't really know what plants do. So did you learn about photosynthesis when you were in school?
Yes. Yep.
So what you learned there is accurate and true, but it's not everything.
Oh yeah, that's what it seemed like. It seemed like a few steps were cut out because it seemed very complicated. But it was more like, here's a definition of it, and here's a couple like flyover steps of what happens. But this didn't stick with me really. Like I don't really remember that very well, to be honest with you.
Right.
But I also just don't remember it being very detailed.
Right. So they probably did simplify it down for your textbooks. You learn more of the full process when you get into higher level biology classes. I took AP biology so long ago, and that was sort of the end of me caring about photosynthesis until I got to this lab. They've done a lot more work on bacteria that do photosynthesis, and so they understand even more than what you learn in the highest level of biology classes.
Okay.
But we still don't know everything. We don't really understand how to recreate what plants do, which I think is good for the hubris of scientists. We can do a lot, but we can't.
Not everything.
We
Yeah.
can't do everything. We can't do what nature is already killing us at.
Yeah.
So nature is pretty amazing. But the basic idea of what happens in photosynthesis and that we try to recreate in my lab is sunlight is absorbed. And that sunlight is energy. The molecules that absorb the energy have electrons that are excited. We've talked about how electrons will take in energy and jump up to higher shelves, kind of. So they take in energy, jump up to higher shelves. And when that energy is excited, when the electron is excited and it's holding energy, that energy is harvested in plants.
Okay.
So that's a very, very basic understanding.
Okay.
We try to recreate that in the lab that I did my undergrad research in. So we aimed to design and then make molecules that have similar properties to what we see plants do in photosynthesis, and then optimize those to be the best they can be so that others who build solar cells and commercialize them have that body of knowledge available.
Yeah.
That's what we did.
So it sounds like the basic main thing to take away from photosynthesis is the fact that because there's energy in sunlight, in ultraviolet rays, all that stuff, whatever's happening, it excites the electrons in, we're talking about plants, right? Still. So in the leaf of a plant or whatever. And that those electrons then, as they're excited, go up to a higher energy shelf. And because of that, there's like actual energy that can be then taken in and kept.
Right.
So it's not just like a temporary thing that's like, oh, they're excited, now they're not. It's like they're continually excited because there's continually sunlight on them, and it allows energy to be like taken in by the plant.
The question about if they're excited and they're not, we're going to talk about that more.
Okay.
I can just get into it now. So they're excited, and the amount of time that they're excited is key to making better solar cells so that you have longer time to excite it. But it is on a very short scale, like smaller than nanoseconds. Very, very short scale.
So it's just happening over and over then in that case? Oh.
And there's lots of electrons that are being excited, coming
Got
back
it.
down, being excited, coming back down.
Okay.
Some are coming up, some are coming down. I don't have intimate knowledge about electrons because I've never shrunk down to the size of an electron to be there, but that is my understanding.
Are they friendly or?
Yeah, I wish it would be incredible as a chemist to be able to be shrunk down to the size of an electron and just look, because we know a lot and we have all kinds of different models of how electrons move, and really they're constantly in motion and they're in a cloud and a possibility of where they could be. And sometimes they can go from one place to another, even though they have no possibility of being anywhere in between. It's amazing.
Yeah.
I wish I could just get down on that level and see what was going on.
That's some magic school bus stuff right there.
I know.
Like they did that stuff, which obviously they're like, it's just a show, but it would be so helpful to do that, or just to have somebody with the knowledge that we do have to just go ahead and make some illustrations like that, or make some sort of, and maybe they actually did do that
would be helpful
on that show.
I don't know if anyone's made illustrations of that, but electrons are just very interesting.
Yeah.
They drive all of organic chemistry, but so we know we can make best guesses based on experimental data that we do have about the way that they move and act. But I would say no one can be 100% sure, because we've not dug in. So we know a lot about them, but we don't know everything. Again, that's the theme of today's episode.
Yeah.
Okay, so in our research, we worked on making molecules that were improved in 3 ways.
Okay.
So one, they could absorb all of the sun's energy.
Okay.
We talked about the electromagnetic spectrum and how there's this visible light section and there's UV also. A lot of that comes from the sun. So if you can have an antenna, as it were, that can absorb energy from all over the spectrum of light that the sun gives off, you're going to be a more efficient harvester of the sun's light.
Got it.
So that was really what I worked on, was expanding the area on which the sun could be absorbed, the sun's light could be absorbed.
Yeah.
The second thing we do is what we just talked about, that we want the electrons to get excited very quickly and stay excited for as long as possible before relaxing back down to the ground state. It's called the excited state and the ground state. So there's a maximum opportunity to harvest their energy.
Got it.
So that's the basics of what I did my research on and the basics of how solar cells work. What happens after the energy is excited is it's harvested and stored. And I worked very little on that part of solar cells. I basically built organic molecules that could absorb a sun's energy and gave them to someone else to work on turning them into solar cells. But my understanding is that the harvesting of the energy at this time is not the limiting factor in turning just everything into solar panels. Actually, it's hard to store solar energy.
Interesting.
So I'm not
Like
an
the
expert
batteries
in this
that
part.
they try to like have charge up with the solar energy aren't great, or just they're inefficient or something like that.
I think it's hard to be able to store them in the quantities you would need to fuel massive amounts.
Right.
So I did not do research to confirm this, but anecdotally, I was told by someone who lives in California that actually they will turn off the solar farms when they're producing too much energy, because it's easier to turn off the solar farms than it is to turn off the fuel burning energy hubs.
Oh, interesting.
So those can be stored and relied upon all the time because we can always store fuel. Whereas solar energy is essentially only usable when it's not needing to be stored in mass quantities,
Got it.
when it's actively providing energy.
Okay, so it's converted. Is it pretty quickly converted into like what we blanket know as electricity?
That is my understanding, yes.
Okay, so
But
it's just
I'm
the
not
storing.
in the industry.
Right. So storing electricity in batteries is the limiting thing.
Yes, we don't
In
have a
some way.
good method, yes.
Okay.
And maybe I can look into more of that and give you some of the problems of that in the future, but it is a pretty complex problem, so
Yeah.
I don't want to get into that. There are other people who are doing research to understand more about how photosynthesis works by looking at the plants, whereas we are basically designing these molecules so that we can imitate how plants work and learn more about the transfer of electrons and how to optimize that without looking at the plants themselves.
Yeah. Even just as a regular Joe, I would say that my perspective is that solar stuff has increased a lot, even if it's not perfect still. We're still just trying to mimic and stuff.
Yeah,
It's become much more every day in my
Yes.
lifetime, obviously,
absolutely.
especially in a way that's kind of cool. Like, it's not perfect yet, but to a lot of us, it's like, whoa, sweet. I have
Yeah.
this thing that can charge my phone and it's solar.
Yes.
Or like I used unfolding solar panel things to charge camera batteries with my previous job when I was out in the middle of
Yeah.
nowhere in Africa or wherever.
Yeah.
So it's already super helpful,
Yes.
even if it's not perfect. So that's kind of mind blowing. It's kind of cool that we're already learning that much, even if it could be way, way, way better in
Yes.
the future.
Well, and usually whenever I gave my presentation, for example, for my research, I'd always start by saying there are other types of energy, but our world energy demand is always growing. And we have non-renewable resources, but current solar panels are using some heavy metals that aren't incredibly safe. They're basically being produced by methods that are non-renewable, even though once they're made, they can harvest a renewable energy source. The making of the solar panels isn't optimal.
Okay.
And there are a lot of places that cannot use an energy grid. So up in really mountainous regions or really remote places, it would be insanely ineffective to build a grid out to those places.
Right.
So actually, there's a book that my sister shared with me called Drawdown. And that book showed that they are currently giving solar panels that are independently functioning to families in the mountainous regions of Bolivia so that they can basically have an improved standard of living.
Yeah.
They would never be able to get on a grid all the way up there.
Right.
So solar panels have the power to really change a lot about the way that the world is right now. And if we just harvest the sun's energy, there's some crazy statistic. I gotta look it up. It's amazing.
Okay.
Okay. I believe the statistic is that if we could harvest the amount of energy, 100% harvest the amount of energy that hits the earth in 1 hour, you can power the earth for a year.
Oh my gosh.
All the world's energy demands for a year. That might not be it exactly, but it is close to that. There's a similar one, I think, that says all of the sunlight that hits the Sahara Desert for 3 hours would power the Earth's energy demands for a year.
That's crazy.
There
even
is
if it's
so
not
much power.
Yeah, even if that's not perfectly accurate, it helps me understand like the level of potential is so high, which I think I've always hoped that was the case, because just the idea of harnessing energy from the sun is so cool.
Yeah.
It's like, wow, that sounds perfect. Let's do it. Like,
Yeah.
I mean, we have a reliable schedule that the sun keeps pretty much. We keep, I guess, really, the earth keeps. Whereas like other things like wind, energy, or whatever, those can be temperamental.
Very intermittent. Yeah.
One thing I thought of when you're talking about remote solutions for power, when we were in New Zealand, there's an area called Milford Sound. It's really, really famous. It's a really sharply cut, narrow, glacier cut kind of bay thing. And it's remote enough to even get there for a long time was really hard. They finally made a tunnel, but the roads are treacherous, so you have to close them a lot. But the people who work in that area for doing like boat tours or hotels or whatever, they have to live there basically.
Right.
And there's no way to get a power grid out there. It would not be worth it at all.
Exactly.
So they actually do all their power for that little town off of a waterfall and stream right near there, that they have a, whatever you call that it spins a turbine or whatever.
I believe it's hydrofuel. Or tidal.
It powers the whole little community, which is crazy. And I didn't really think about it, but there were no power lines along the way. And when on the way back, I was looking, and it took us forever to ever see any power lines again. So it's like, it's not just off the grid a little bit because it's behind a mountain. It's way out. So it's fascinating.
That is amazing. Yeah.
Obviously, it's a different kind of power, but I was thinking about that with the remoteness thing that you're talking about.
Well, and that is the really cool things about solar energy, is that it's renewable with a ton of power. It can be very cost effective. That book also told a story that businesses who went beyond what they were supposed to in terms of their emissions, greenhouse gas emissions, were fined. And they used those fines to pay to put solar panels in low income areas in California.
Nice.
And then those families' bills went down significantly, being very cost effective once you install the solar panels, and very widely distributable, off the grid, and obviously more environmentally friendly than burning fuel. So that is the really cool thing about solar energy. And it's really fun to know that I got to be a part of the process of optimizing it. On that note, do you want to hear a cool story about my friend E?
Yes, absolutely.
My friend E, she is a friend of the podcast. She's a colleague that I run things by often. She defended her PhD and now is a doctor.
Whoa.
Dr. E.
Does she make you call her that now?
No. Her last name is Who, so she's Doctor Who.
Whoa.
I know.
Is it spelled the same way?
No.
Okay, I didn't think it would be, but...
So she defended her dissertation recently, and it was so fascinating because she actually built a new class of compounds that, if it can be optimized properly and converted for use in solar cells, could change a lot about the way solar
Whoa.
cells are made in the future. Yeah, she did incredibly interesting work building a molecule and then tweaking it so that it could absorb more energy on the sun that people thought it wasn't really possible to build. And she did it. She went to a conference and presented it, and they told her they didn't believe her, even though she had proof. So she went back and essentially grew, it's called growing crystals. If you've ever made rock candy, it's the same idea, but it's much more complicated with molecules that are that big. But grew crystals so that someone could do basically an x-ray of the crystal and prove beyond a shadow of the doubt that she made the thing she made.
Wow.
Which she did, and now they all have to believe her.
Nice. So she just told them, what's up? She's like, I'm sorry, check out these crystals.
She didn't say it exactly like that. As I would have surely been like, in your face.
Yeah.
But I was like that for her. I was so excited that she did it. I thought, that's amazing. She did something so hard that other people who work on the same type of chemistry had a hard time knowing she did it.
Yeah.
And it had very good results in terms of the efficiency for solar cells. So that was a really cool thing to get to witness and be a part of. So congratulations, E, for becoming a doctor and contributing so well to the field.
That is awesome.
That's it. That's the basics of how solar cells work and the type of research I did when I was working on my master's degree.
Okay, so the sun.
Yes.
It's spitting out its light and energy and all kinds of things that which we can see, like light, and things we cannot see, like UV. Spitting it out all over the solar system in every direction, which is nice, and it hits our planet for the part that we're on for half of a day. And if we have a solar cell or like a plant,
Right.
that is able to have in a solar cell situation, it has some element, some molecules you guys have been able to
Molecule, yes.
pack together.
Definitely don't say element because that's one
Right.
substance
That'd be one on its
the
own.
periodic
Okay,
table.
got
Yes.
it. So a molecule
A molecule.
that when the sun hits it, the light and the rays and the energy from the sun are hitting it, it excites the electrons in that molecule. And that excitement is the taking in of the energy that's hitting it.
Right.
And then from there, that energy becomes electricity and, Lord willing, stored in some battery or capacity or whatever.
Right.
Or in a plant, it
As
is
food.
as food for the plant.
Yeah, so I think in a plant, I don't think it becomes electricity the way
Right.
we think of it. It's just the energy is captured and stored. They use that energy to make sugars or carbohydrates or whatever.
Yeah.
But that's a really great explanation and understanding.
And the work you did was to improve solar cells in the 3 ways, which are hoping to broaden the amount of energy that can be captured by the sun. So not just like a narrow on the spectrum, trying to widen that as much as possible so that
Right.
as much of a range, kind of like trying to get a bigger fire hose or something like that,
Right.
rather than a small garden hose.
Right.
You can widen it and to capture as much as you can. And then also improving how quickly the electrons in those solar cells can get excited and then how long they
Yeah.
can stay excited.
Yeah.
And all those things combined would improve how much electricity we can get from the sun.
Right.
Dude, that's kind of crazy.
And then we need to work on doing what plants do, where they take the energy
Store it.
and store it in nice carbs that we can eat.
So what's interesting to me about that is as a user, I've known that batteries aren't great, and that we're trying to improve them. So it's like whether it's as simple as like, oh man, the remote is out of batteries again on your TV like, when we were kids, or like now our phones. I mean, even though they get better, it's like, oh, my phone's dying. So I've known, I guess, that batteries aren't like perfect yet, you know, but thinking that it didn't really occur to me that with the whole solar panels, solar cells system, that one of the biggest areas in need of improvement would be just how to store the energy better.
Yeah.
That just didn't occur to me before.
It's very interesting. I am fascinated by all of that process and how we are working to move away from non-renewable energy resources towards renewable energy resources and what the challenges are. And it's just been a long, storied, very interesting process. You got it. That was a great explanation. So if just for you guys to look at on the social media, I'm going to put some pictures of a molecule that I actually made that does this. It's beautiful. It's red, it's shiny and metallic. And when it's dissolved in liquid, it is this great teal color.
Interesting.
You can even see it absorbs energy and then emits energy back out as a different color. So that's really cool. So I'll post some pictures of that just so you guys can see what I actually made in the lab. But that's pretty much it. Do you want to say something that made you happy today, Jam?
Yes. So what made me happy today is, or this week or whatever, we just had a Friendsgiving gathering.
Yeah.
Which was really fun. Had some awesome food.
Oh yeah, very good food.
It's great when a lot of your friends are good at cooking or baking or whatever. Mm-hmm. You should want to spend time with them anyway, in some capacity. But when it comes down to something like a Friendsgiving meal, potluck, where everybody brings something, it's definitely nice to have buddied up with friends who can cook well.
Oh
so
yeah,
that was really fun, really enjoyable.
Really fun.
I'm going to be dreaming about that meal for a while.
Yeah, there was the Brussels sprouts were good. The carrots were good.
Mm-hmm.
The corn was good.
The corn thing, the sweet potatoes.
Oh, the roast beef.
Yes.
There was in your traditional. We had turkey.
Yeah.
Jam's wife makes a very good turkey.
She really does. It was great every time. It's nice to have something like that you only have once a year because then you really look forward to it.
Yeah.
And it really hit the spot.
Yeah, it was great. Can that be my thing I'm happy for too?
I think so. It feels like if you don't choose the same thing, then whatever you say, unless it's really, really cool, won't be as cool as and delicious sounding as this. So
well, how about I say that's my number one.
Okay.
But as a number two,
Uh-huh.
I am about to be finished with the project that I was working on while you were in New Zealand.
Uh-huh.
And I'm ahead of schedule. I've never been this ahead on anything ever except my master's thesis and presentation.
Uh-huh.
But I'm going to do the presentation in about 24 hours and then I'll be finished. And that will just be a very large weight lifted off of me because
nice.
it's 50% of my final grade.
Oh my gosh. That's awesome.
I'm very excited about that, but also about Friendsgiving. That was something that really warmed my heart in a special way.
Yeah.
So.
Yeah. And I used some chemistry to make some wassail. I tried to use all my chemistry knowledge, put it in, channeled it into some wassail.
Yes, and our friend Sam prompted a whole conversation about our show.
Yeah, he
when
did.
He was making mashed potatoes.
Yeah, he started talking about salt in water and how it affects boiling and all of that stuff, which is in a previous episode. If you haven't listened to, go listen to Why Did My Pot Never Boil?
And then Jam gave a quick science lesson in the middle of the Friendsgiving kitchen. So
That's true. Yeah. I was like, this
really
is an
fun.
opportunity to prove that I learned and retained this information.
and to get others excited.
Yeah, absolutely.
That was really fun. Well, thank you so much, Jam, for learning.
Anytime.
And thank all of you guys for listening. And I'd like to thank also my references this week. I primarily used prior knowledge, but I did use information from Drawdown by Paul Hawken.
Mm-hmm.
And then it is not quantifiable, but by the vast number of interactions that I've had with scientists who are experts in this field over the course of my time working in it. So that's hard to put a reference to.
Yeah.
But that is the primary source for my information.
Got it. And you're referencing your own document as well, which is prior knowledge, but your own
Oh, that's true. I did use my own thesis
Yeah.
to refer back to.
Yeah.
That sounds fun and weird, but I did do that. I looked at it. So those are all the references that I use this week.
Melissa and I have a lot of other ideas for topics of chemistry in everyday life, but we want to hear from you. So if you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share thoughts and ideas. And if you enjoy this podcast, you should tell one of your friends about this podcast today. Just one. And if everybody did that, we'd actually kind of double in just one day. But
And that would help us share chemistry with even more people.
Absolutely. And that's the goal.
This episode of Chemistry for Your Life was created by Melissa Collini and Jan Robinson. Jan Robinson is our producer, and we'd like to give a special thanks to A. Collini and In Newell, who reviewed this episode.